Entity relationship model.
In software engineering, an entity relationship model is a data model for describing the data or information aspects of a business domain or its process requirements, in an abstract way that lends itself to ultimately being implemented in a database such as a relational database. The main components of ER models are entities and the relationships that can exist among them. Entity relationship modeling was developed by Peter Chen and published in a 1976 paper. However, variants of the idea existed previously, and have been devised subsequently, such as supertype and subtype data entities and commonality relationships.
Overview.
An entity relationship model is a systematic way of describing and defining a business process. The process is modeled as components, entities, that are linked with each other by relationships that express the dependencies and requirements between them, such as, one building may be divided into 0 or more apartments, but one apartment can only be located in one building. Entities may have various properties, attributes, that characterize them. Diagrams created to represent these entities, attributes, and relationships graphically are called entity relationship diagrams. An ER model is typically implemented as a database. In the case of a relational database, which stores data in tables, which represent the entities. Some data fields in these tables point to indexes in other tables. Such pointers represent the relationships. The three-schema approach to software engineering uses 3 levels of ER models that may be developed. The first stage of information system design uses these models during the requirements analysis to describe information needs or the type of information that is to be stored in a database. The data modeling technique can be used to describe any ontology, that is an overview and classifications of use terms and their relationships, for a certain area of interest. In the case of the design of an information system that is based on a database, the conceptual data model is, at a later stage, usually called logical design, mapped to a logical data model, such as the relational model. This in turn is mapped to a physical model during physical design. Note that sometimes, both of these phases are referred to as physical design. It is also used in database management system.
Entity relationship modeling.
An entity may be defined as a thing which is recognized as being capable of an independent existence and which can be uniquely identified. An entity is an abstraction from the complexities of a domain. When we speak of an entity, we normally speak of some aspect of the real world which can be distinguished from other aspects of the real world. An entity may be a physical object such as a house or a car, an event such as a house sale or a car service, or a concept such as a customer transaction or order. Although the term entity is the one most commonly used, following Chen we should really distinguish between an entity and an entity type. An entity type is a category. An entity, strictly speaking, is an instance of a given entity type. There are usually many instances of an entity type. Because the term entity type is somewhat cumbersome, most people tend to use the term entity as a synonym for this term. Entities can be thought of as nouns. Examples: a computer, an employee, a song, a mathematical theorem. A relationship captures how entities are related to one another. Relationships can be thought of as verbs, linking 2 or more nouns. Examples: an owns relationship between a company and a computer, a supervisor's relationship between an employee and a department, a performs relationship between an artist and a song, a proved relationship between a mathematician and a theorem. The model's linguistic aspect described above is utilized in the declarative database query language ERL, which mimics natural language constructs. ERL semantics and implementation are based on reshaped relational algebra, or RA, a relational algebra which is adapted to the entity relationship model and captures its linguistic aspect. Entities and relationships can both have attributes. Examples: an employee entity might have a social security number, SSN, attribute. The proved relationship may have a date attribute. Every entity, unless it is a weak entity, must have a minimal set of uniquely identifying attributes, which is called the entity's primary key. Entity relationship diagrams don't show single entities or single instances of relations. Rather, they show entity sets and relationship sets. Example, a particular song is an entity. The collection of all songs in a database is an entity set. The eaten relationship between a child and her lunch is a single relationship. The set of all such child-lunch relationships in a database is a relationship set. In other words, a relationship set corresponds to a relation in mathematics, while a relationship corresponds to a member of the relation. Certain cardinality constraints on relationship sets may be indicated as well.
Mapping natural language.
Chen proposed the following rules of thumb for mapping natural language descriptions into ER diagrams. Physical views show how data is actually stored.
Relationships, roles and cardinalities.
In Chen's original paper he gives an example of a relationship and its roles. He describes a relationship marriage, and its two roles husband and wife. A person plays the role of husband in a marriage, relationship, and another person plays the role of wife in the same marriage. These words are nouns. That is no surprise. Naming things requires a noun. However, as is quite usual with new ideas, many eagerly appropriated the new terminology but then applied it to their own old ideas. Thus the lines, arrows and crow's feet of their diagrams owed more to the earlier Bachmann diagrams than to Chen's relationship diamonds. And they similarly misunderstood other important concepts. In particular, it became fashionable, now almost to the point of exclusivity, to name relationships and roles as verbs or phrases.
Role naming.
It has also become prevalent to name roles with phrases such as is the owner of and is owned by. Correct nouns in this case are owner and possession. Thus person plays the role of owner and car plays the role of possession rather than person plays the role of, is the owner of, etc. The use of nouns has direct benefit when generating physical implementations from semantic models. When a person has two relationships with car, then it is possible to generate names such as owner person and driver person which are immediately meaningful.
Cardinalities.
Modifications to the original specification can be beneficial. Chen described look-across cardinalities. As an aside, the Barker-Ellis notation, used in Oracle Designer, uses same-side for minimum cardinality, analogous to optionality, and role, but look-across for maximum cardinality, the Crowsfoot. In Mirais, El-Misri and Navov and others there is a preference for same-side for roles and both minimum and maximum cardinalities. Recent researchers, Fenera, Dallaire al. have shown that this is more coherent when applied to NR relationships of order greater than 2. In Dallaire al. one reads a look-across notation such as used in the UML does not effectively represent the semantics of participation constraints imposed on relationships where the degree is higher than binary. In Fenera it says problems arise if we operate under the look-across semantics as used for UML associations. Hartman investigates this situation and shows how and why different transformations fail. Although the reduction mentioned is spurious as the two diagrams 3.4 and 3.5 are in fact the same, and also as we will see on the next few pages, the look-across interpretation introduces several difficulties which prevent the extension of simple mechanisms from binary to NR associations. Chen's notation for entity relationship modeling uses rectangles to represent entity sets, and diamonds to represent relationships appropriate for first-class objects. They can have attributes and relationships of their own. If an entity set participates in a relationship set, they are connected with a line. Attributes are drawn as ovals and are connected with a line to exactly one entity or relationship set. Cardinality constraints are expressed as follows. A double line indicates a participation constraint, totality or subjectivity. All entities in the entity set must participate in at least one relationship in the relationship set. An arrow from entity set to relationship set indicates a key constraint, that is injectivity, Each entity of the entity set can participate in at most one relationship in the relationship set. A thick line indicates both, that is projectivity. Each entity in the entity set is involved in exactly one relationship. An underlined name of an attribute indicates that it is a key. Two different entities or relationships with this attribute always have different values for this attribute. Attributes are often omitted as they can clutter up a diagram. Other diagram techniques often list entity attributes within the rectangles drawn for entity sets. Related diagramming convention techniques. Bachman notation, Barker's notation, Express, IDEF1X, Martin notation, Min, Max, notation of Jean Raymond Abriol in 1974, UML class diagrams, Mirais, object role modeling.
Crowsfoot notation.
Crowsfoot notation is used in Barker's notation, structured systems analysis and design method, SSADM, and information engineering. Crowsfoot diagrams represent entities as boxes, and relationships as lines between the boxes. Different shapes at the ends of these lines represent the cardinality of the relationship. Crowsfoot notation was used in the consultancy practice CACI. Many of the consultants at CACI, including Richard Barker, subsequently moved to Oracle UK, where they developed the early versions of Oracle's case tools, introducing the notation to a wider audience. The following tools use Crowsfoot notation: ARIS, System Architect, Visio, Power Designer, TOE Data Modeler, DZIGN for databases, DevGems Data Modeler, OmniGraffle, MySQL Workbench and SQL Developer Data Modeler. CA's ICASE tool, CAGen, also known as Information Engineering Facility, also uses this notation. Historically, XA Systems Silver Run LDM, Logical Data Model, also supported this notation.
ER diagramming tools.
There are many ER diagramming tools. Free software ER diagramming tools that can interpret and generate ER models and SQL and do database analysis are MySQL Workbench, formerly DB Designer, and Open Model Sphere, open source. A freeware ER tool that can generate database and application layer code, weak services, is the RISE editor. SQL Power Architect, while proprietary, also has a free community edition. Proprietary ER diagramming tools are Evolution, ER Studio, Owen, DZIGN for databases, Magic Draw, Mega International, ModelWrite, Navicat Data Modeler, OmniGraffle, Oracle Designer, Power Designer, Prosa Structured Analysis Tool, Rational Rows, Software Ideas Modeler, Sparks Enterprise Architect, SQLYOG, System Architect, TOE Data Modeler, and Visual Paradigm. Free software diagram tools just draw the shapes without having any knowledge of what they mean, nor do they generate SQL. These include Creately, YEd, Lucidchart, CalligraFlow, and Aya.
ER and semantic modeling.
Peter Chen, the father of ER modeling, said in his seminal paper, "He is here in accord with philosophic and theoretical traditions from the time of the ancient Greek philosophers, Socrates, Plato and Aristotle, 428 BC, through to modern epistemology, semiotics and logic of Park, Frege and Russell. Plato himself associates knowledge with the apprehension of unchanging forms. The forms, according to Socrates, are roughly speaking archetypes or abstract representations of the many types of things, and properties, and their relationships to one another." In his original 1976 article, Chen explicitly contrasts entity relationship diagrams with record modeling techniques. Several other authors also support his program. A semantic model is a model of concepts. It is sometimes called a platform-independent model. It is an intentional model. At the latest since Carnap, it is well known that an extensional model is one which maps to the elements of a particular methodology or technology, and is thus a platform-specific model. The UML specification explicitly states that associations in class models are extensional, and this is in fact self-evident by considering the extensive array of additional adornments provided by the specification over and above those provided by any of the prior candidate semantic modeling languages. UML is a data modeling notation, part 2 inches.
Limitations.
EA models assume information content that can readily be represented in a relational database. They describe only a relational structure for this information. They are inadequate for systems in which the information cannot readily be represented in relational form, such as with semi-structured data. For many systems, possible changes to information contained are non-trivial and important enough to warrant explicit specification. Some authors have extended EA modeling with constructs to represent change, an approach supported by the original author. An example is anchor modeling. An alternative is to model change separately, using a process modeling technique. Additional techniques can be used for other aspects of systems. For instance, EA models roughly correspond to just one of the 14 different modeling techniques offered by UML. EA modeling is aimed at specifying information from scratch. This suits the design of new, standalone information systems, but is of less help in integrating pre-existing information sources that already define their own data representations in detail. Even where it is suitable in principle, EA modeling is rarely used as a separate activity. One reason for this is today's abundance of tools to support diagramming and other design support directly on relational database management systems. These tools can readily extract database diagrams that are very close to EA diagrams from existing databases, and they provide alternative views on the information contained in such diagrams. In a survey, Brody and Liu could not find a single instance of entity relationship modeling inside a sample of 10 Fortune 100 companies. Badia and Lemire blame this lack of use on the lack of guidance, but also on the lack of benefits, such as lack of support for data integration. The Enhanced Entity Relationship Model, EER modeling, introduces several concepts which are not present in EER modeling, which are closely related to object-oriented design, like ISA relationships. For modeling temporal databases, numerous ER extensions have been considered. Similarly, the ER model was found unsuitable for multidimensional databases, used in OLAP applications. No dominant conceptual model has emerged in this field yet, although they generally revolve around the concept of OLAP cube, also known as data cube within the field.